Welcome, this is Dr. Plague. I know it's been a while, but I'm back. I had to wait to see if I was renewed for another season, and I was. Nah, I'm just joking. I've been quite busy, so breaks like that will happen. Anyway, today I'll be giving an introduction to some upcoming videos on composite video generation. I'll also be demonstrating some various ways we can view composite video signals on a variety of oscilloscopes. We'll be using some digital scopes, and I'll finish off with an old analog scope. Now, before we move on, I just want to quickly address something. You know, I'm always going to get those comments from people saying something like, "Hey, Dr. Plague, this is ridiculous. Composite video is old and obsolete. Why are you stuck on this old stuff? Let's get over it and move on to something more relevant to present-day technology." But there's so much more to learning about and designing composite video circuits than just the fact that it's old. We can learn a lot about analog encoding, timing, synchronization, bandwidth-limited modulation, filtering, impedance matching, and noise tolerance, to name a few things. If you can design a stable composite video generator, then you've touched almost every fundamental concept in analog and mixed signal electronics. Generating a composite video signal forces you to think in microsecond level timing, line and field structure, sync pulse shaping, color burst phase relationships, clock generation, and jitter. It's one of the few analog systems you can fully understand end to end. You can literally draw the waveform on paper and then build the circuit that produces it. That's rare today. It's a very easy way to give a homemade computer a real display. It's a gateway to understanding modern video. It teaches us luminance and chrominance separation, bandwidth allocation, modulation schemes, sync encoding, and color spaces. Most of all, it's fun, and engineering needs more of that. Obsolete technologies often become the best teaching tools. Composite video is one of the few display standards simple enough for a hobbyist to generate from scratch, yet complex enough to teach real engineering. That's why it's worth learning, and it's embedded in our history. Do we stop teaching history because things are old and outdated? No, of course not. It has historic merit. For those that want to critique it, well, that's your thing. My thing is to embrace it. Now, there are many ways we could build a composite video generator circuit, and we'll look at some different designs in upcoming videos. The two main designs we'll be exploring are processor-based generators and discretely built generators with no processor. Now, if we want to take the easy way, we could simply use some type of a processor to generate a composite video signal. What we'll probably use will be the ATmega1284, which I've used quite frequently in the past. You could also use a smaller processor such as an ATmega48. In fact, I used that processor in a simple homemade video game circuit that I made decades ago. I also showcased that design in a past video on homemade video games, in part 2 that is. So if you haven't seen that video, then you might want to go back and check it out. Now, if you're not familiar with the ATmega48, you may know of the ATmega328, which is its bigger brother, if you will. The ATmega328 was used on the Arduino Uno and has much more memory than the Mega 48. The Mega 48 only has 4K of flash, while the Mega 328 has 32K. But even with only 4K, I was able to make a very capable video game circuit. It wasn't spectacular by any means. It was probably similar to the capabilities of the old Atari 2600 system. So, if I was able to do something like that with only 4K, then imagine what you could do with 32K. Now, the first designs that I'll start out with won't use any type of a processor. We'll just start designing circuits on breadboards. We'll also look at some dedicated ICs to get some ideas on how they function. In the next video, I plan on showing you the very first standalone composite video generator circuit that I ever built. It was a very simple design. It didn't use any prefabbed video generator ICs, or any type of processor for that matter. The only ICs it used were 74 series logic and a memory chip, because, well, we need some type of memory to store the image that will be displayed. And it was all built on one small half-sized breadboard like this. Well, it would have required more space to build if it wasn't for some, let's call it design decisions. You'll have to see it to believe it. Now, the circuits that I'll be building up in future videos won't be be-all, end-all designs. They'll be something to give you ideas, so you can design your own circuits. Now, don't get me wrong, the circuits that I'll be designing and building will work just fine. They just won't be the best designs. They're meant to give a starting point for those that have no clue how to begin developing composite video generating circuits. You can certainly use them as is, or better yet, you can come up with improved designs for your own use. Whether you're trying to interface a homemade computer to a TV or whatever. Now, let's talk about viewing composite video signals on an oscilloscope. If you're going to work with generating composite TV signals, then I highly recommend that you have an oscilloscope that you can use. You want to make sure the signal you create is correct before connecting your circuit up to the composite input of a TV or video monitor. Digital scopes are ideal for this task, but even an older analog scope can be useful. If you're not familiar with how to display these signals on a scope, then hopefully one of these methods will work for you. I'll be demonstrating viewing composite video signals on 5 different oscilloscopes. I'll start out with my best scope first, and work my way down to my analog scope. And by the way, the first 2 scopes that I'll be showing have video output ports on them, so I'll be capturing that video and superimposing it over the oscilloscope screens. I still want to show the scopes themselves so you can see the knobs and buttons as I play around with them. It'll look a little odd, but this way the camera won't pick up any glare on the screens and such. I won't be able to do that with the other 3 scopes. So, this is a Tektronix MDO3000 series scope, and it's not an entry-level scope. This thing has some really cool features for viewing video signals that you won't find in most other scopes, and I'll just touch on it today. Now, for demonstrating this, I'll use this here Blu-ray player as the source of a composite video signal. Now, we need to somehow connect the composite output from the Blu-ray player to the oscilloscope. There are a number of ways we can do this. This Tektronix scope allows us to select the termination impedance, but not with this probe connected. So first, I'll disconnect this probe from the scope. Now, notice that we can select from 1 megohm, 75 ohms, and 50 ohms. Composite TV inputs have an impedance of 75 ohms, so we want to select 75 ohms. You're most likely not going to have this option on lower-end scopes. I'll show some things you can do a little later if you don't have this option. We need to make sure there are no series resistances with our method of connecting the signal output to the scope input. You might consider connecting a switchable ×1 ×10 probe and setting it to the ×1 position. In the ×10 position, there will be a 9 megohm resistor added in series to the scope impedance, and using the ×1 option removes that resistance. But is the resistance really 0 in ×1 mode? No, there is usually some amount of resistance. In this case, it is much higher than the 75 ohms we need. Besides, even if there was 0 ohms, we still wouldn't want to use a ×1 probe. The characteristic impedance of the probe cable is wrong, and it isn't designed to carry current. Remember, the load is now in the scope, so the current would travel through the probe cable, although it's not very much. So, what do I suggest? Well, you have some options. I'll show how we can use an actual scope probe a little later. But for now, the option I'll be showing first is to use one of these inexpensive BNC male to RCA female adapters. Now we can simply connect the RCA video cable directly from the Blu-ray player to the scope input. Make sure the probe attenuation is set to 1 times, and not something like 10 times. These RCA video cables are usually designed to have about 75 ohms of characteristic impedance, so this should work out great. Now, before we get going, I'm going to set the termination impedance of the scope to be 1 megohm first, to show you what could happen if you don't use 75 ohms. The Blu-ray player is on, so let's plug it in. In this case, the signal looks like a straight-up DC voltage, around 2.6 volts or so. Now, let's switch to 75 ohms. That looks a little better. Let's zoom in on the voltage a little bit. Now we can freeze the image and zoom into the timeline a bit and look around. It kind of looks like a composite video signal, but I think we can do better than this. Let's go into the trigger options and look at what we have. Look there, there's a video option. Let's choose that one. With this scope, we can choose all kinds of video standards, even custom bi- and tri-level signals. But what I want is NTSC 525i. Now look at that, the signal is stable. And we can use the Trigger On feature to choose the line number we want to view. Then we can scroll through different lines. The first ones are part of the vertical retrace signal. Then we get to the blank lines. And look at this. Once we get to line 20, we have some interesting things going on here. And line 21 is interesting too. This is actually for closed captioning. After that, we have what looks like picture lines. And we can zoom in a little. Here's the color burst signal. And we can see that it alternates in polarity, which is normal. And we can take measurements and such. In my old video on the Composite TV Signal, I mentioned that there is a breezeway of about 0.6 microseconds. Let's see how close this is. Yeah, that's fairly close. And we can see that the voltage level here is around the 286 millivolts that I mentioned in the old video. Now, this scope can do something that most scopes can't. This is a rare feature. If we go into the test options here, we can find an application for video picture. Now we can turn the display on. Let's see here. There we go. And look at that. This scope has raster image reconstruction. We can see the image being transmitted by the composite video signal. It is in black and white, but still an impressive feat for an oscilloscope. Awesome! So we can lock into the signal, select specific lines to view, take measurements, and reconstruct and display a recognizable image from the composite video signal. Fantastic! And if you don't have one of these BNC to RCA adapters, you could also use a BNC to alligator clips cable if you have one. We can see the resistance is negligible. They work just fine for this purpose. Now, let's take a look at this here scope. It's the 12-bit Rigol DHO924S. It's a fairly popular entry-level scope. Now, this scope does not have internal 75 ohm termination. You won't see that in most entry-level or hobby-grade scopes. I've shown that we need that termination impedance with my Blu-ray player. So, what can we do? Well, if we don't have internal impedance, then we need external impedance. We can actually use one of these standard scope probes if we place the impedance at the point where we probe it. You may have seen me do this in some past videos. I'll just place a 75 ohm resistor here when I connect up the scope probe. And make sure you're connecting the scope probe ground to the right place. The outer conductor on the RCA connector should be ground, and the inner conductor should be the signal. But it's your responsibility to make sure your connections are correct. And if we're making our own circuits on a breadboard, then it'll be easy to add a 75 ohm resistor to the breadboard for probing. Now, if we turn on the Blu-ray player, then we can see what looks like a composite video signal. So this connection works fine. Now, an alternative to using a resistor like this is to use a feed-through terminator like this one. Unfortunately, this one is 50 ohms, and I don't have any 75 ohm versions to show you. Now, these can be quite expensive. So what you can do is get one of these cheap 75 ohm terminator plugs and a BNC T adapter like this. We can then connect the BNC to RCA adapter to this, add in the termination plug, and connect it directly to the scope. When we do this, we need to change the input to 1x, which is times 1. And I'll put it back to 500 millivolts per division. Okay, let's go to the trigger menu and look at what types we have. There is a video trigger, so let's select that. This scope gives us a selection of standards. Let's look at them. And you can see there is a nice selection similar to the Tektronix scope. I'll leave it at NTSC since I'm based in the US. Then I'll set the level to about 260 millivolts since this signal is entirely above 0 volts. You should adjust accordingly. Get the level somewhere in the sync pulse here. Next, I'll select Line Trigger. Let's zoom out a bit and move this window over. Now, we can use knob number 2 to select the line number to trigger on. Let's check out lines 20 and 21. Those were the interesting lines that we'll try to view on all the scopes. Okay, now we can look at any line that we want and perform measurements and such. Perfect. Let's move on to the next scope. We'll be looking at this Rigol DS1000 series scope, a very popular one among hobbyists. If we're plugging straight in, then we should set the probe to 1x. Next, I'll set the scale to 500 millivolts. Now let's go to the trigger menu and look at the types. Again, we have a video trigger, so let's go down to that. We can choose the standard, and this scope has far fewer to select from, but I'll stick with NTSC. Next, I'll sync on the line. I'll move the trigger up, and we need to change the polarity on this scope, which is opposite from the last scope, but you can try the different polarities until one syncs up. We can zoom out a bit here, and look at lines 20 and 21. And now we can poke around the signal and view any portion of it. Great! Well, let's check out the last digital scope that I'll be demonstrating today. This is the B&K Precision 2190D, and it's the least capable of my digital scopes. So let's see what we can do with this one. Since I'll be plugging straight in, I'll just set the probe to 1x. Let's turn on the player. Some of these lower end scopes may need the amplitude magnified a little more to properly trigger on it. So I'll scale it to 200 millivolts and zoom in a bit here. Let's go into the trigger menu and look at the types. And again, we have a video trigger. So let's select that. We only have two standards on this scope, NTSC and PAL/CCAM. Well, I'll set it to NTSC. I'll set the trigger level until we lock in. Now, let's go view lines 20 and 21. And I can do that with the Select knob. And we can look at different sections of these lines in more detail and such. And there it is. We can do much the same with this scope. Now, most of the benchtop digital scopes out there will have video triggering capabilities. You probably won't find it in handheld scopes, but benchtops will usually have it. Note that the Rohde & Schwarz MX03 series does not appear to have video triggering capabilities. I noticed this when Rohde & Schwarz came out to my place of employment and gave us a demonstration of it. I asked the representative and he told me that it currently does not support video triggering. But some other Rohde & Schwarz scopes do. So if you're in the market for a new digital scope, you may want to check out the capabilities of it before purchasing one. Let's say you do have a digital scope that does not have video triggering. What can you do? Well, most digital scopes have the capability to store a lot of data points, so we should be able to change the record length to something high like 10 megapoints. Now we can just stop and zoom in on it. Here's the vertical sync pulses. And we can now scroll through to look at the various lines, all without needing a special video trigger. The last scope we'll be looking at will be this here old Philips PM3070 analog scope. Now again, this is not an entry-level scope, so it'll have some features that you won't find in those scopes. We're going to be using a feature that we call the delayed time base. This is what it does. Let's say that we have a signal like this, and that we want to zoom into something like this here. We can use the main time base to trigger on this right here. Then, using the delayed time base, we can choose this area and highlight it. Then, we can zoom into that section, and we can then remove this longer signal from the display if we want. Let's look at how to do this on the scope. Now, just a bit of explanation for what you're about to see. I had to dim the lights to get a decent video of this scope's CRT screen. If I add more lighting, then it washes out the traces on the CRT. Also, you may notice some light and dark areas on the CRT screen due to the video frame rate and the speed of the electron beam in the CRT. These are things that show up in the video, but you don't see these issues when looking at the scope in person. Now, this is a very old scope, and it's not operating as stellar as it should anymore. So we'll see if I can get this to work. If I can even remember how to use this antique beast of a machine. So you can see that I have the composite video signal going into channel A here with the 75 ohm terminator plug. First, I'll turn the cursors off. Then remove the text from the screen so the electron beam can concentrate on the signals of interest. Let's set the scale to 500 millivolts. I'll set the trigger mode to trigger instead of auto, so we only display signals that are triggered. I don't want it running continuously in auto mode. Now I'm going to adjust the main time base to 2 milliseconds. This will give us 20 milliseconds across the whole screen, so we'll get most of the 2 fields of a frame. Then I'll set the trigger coupling to trigger on the TV fields, something that this scope is capable of doing. I have the hold off set to its minimum, so it should re-trigger on the same field each time. If we change the main time base, then we may need to adjust the hold off time. For the time base, I'll select the main time base with the intensified section. And let's just turn the intensity up because this can be very hard to see. I'll set the scale of the delayed time base to 20 microseconds. We can see the intensified section here that we want to zoom in on. Next, I'll add in the delayed time base on the screen. And now we can see the zoomed in section. Each time base can have its own trigger, so I'll change the trigger of the delayed time base to the TV line. Now we can scroll around and look at the different composite video lines, kind of like we did with the digital scopes. Here we can see the vertical blanking section. And when we get to the interesting lines of 20 and 21, I'll just remove the display of the signal from the main time base. Perfect! There are our lines of interest. We can play around and zoom into this and stuff. And that's how we can look at the different lines on an old analog scope. Now, bear in mind that entry-level scopes usually don't have delayed time base functionality. It is mostly seen in mid to high-end scopes, usually 100 MHz plus. Same goes for the TV trigger. You're not going to find that on all analog scopes. If you have an analog scope with delayed time base but no TV triggering, we can still look at some of the characteristics of the composite video signal. So again, I'll turn the cursor and text off. I'll just set it to 200 millivolts per division. Then turn triggering on. Let's set it to about 10 microseconds per division. I'll set the trigger coupling to DC and adjust the level. There we go. Now we're locked in. I'll display the signal from both time bases. Now, when we do this, we are triggering on all the lines, so we get a mixture of them all at once. Then zoom in a bit to 1 microsecond per division. We can scroll around and look at different sections of the line. There's the color burst. We can set the trigger to different levels to see the alternating polarities and such. So yeah, there we go. Now, if you don't have delayed time base or TV triggering, you can still look at parts of the signal. I'll turn cursors and text off. Then set it to 200 millivolts. You can set it to your own liking, of course. Turn on triggering. I'll zoom into a line at 10 microseconds per division and adjust the trigger level. Now we're locked in. And we can zoom in to check out the color burst or whatever. So, not as impressive as delayed time base or video triggering, but it still gives you a basic look at the signal. You can also use an external sync separator and trigger on that. I did make a past video on how I designed a simple homemade sync separator, but honestly, that's a little overkill for this. We just want a general view of the signal to make sure there aren't any obvious abnormalities. If we can observe it in more detail, then great, but we can get by with basic capabilities. Okay, well that pretty much covers it for this video. More content will be coming with all kinds of video circuit ideas. Thanks for watching, and I'll see you next time, right here on Dr. Plague.